fun way to put it in the Excel sheet. You need to get your grade, and after the class, today we're going to have a discussion. If you don't have any problem to go over it, if you have any question, I'll be here. I'll just stay here and we'll go over the questions if you have. But right after the class, I'm going to give you the midterm back. The good things about midterm, the grade was not really that good. But the good things about it, every question, I had at least 3 people they got a full grade. So I'm happy, I don't want you to have a question, nobody gets full grade on it, The good thing is in every question, first question I think we had like 15, 16 people they got full grade. The third question I think we had 3, they got full grade. The second one was I think 5 or 6, something like that. I'm not sure I can recall that grade. Number 2, last week. Don't worry about your grade if it's not very good. Let's look at she's going to send you the email to tell you what's the median, what's the average, those kind of thing. And focus on your final for the grade if you want to get a good grade. Maybe some of you are a little bit low. One more thing I was going to say. Grade and sorry?
Will you change the weight on the
what do you mean? No, I'm not going to change the weight. No, the weight is going to change a little bit, yes. So let's say, because initially I said until the end of DC machine it's going to be half and half. Now the weight of midterm is going to be less. I think overall I'm not sure how many percent we had for midterm and final, maybe around
35.
It was only 35, 35. Very, very possible it become 30, 40 or something like that, or maybe a little bit less. Yeah, not 25. It's going to be around 30. It definitely is at least 5% is going to go to the final. We had one person who is Wasim Asifi. He got a 103 out of 100. The 3 is for writing, write-offs. You got the, I'm happy. One person full grade, and he got you can kill him because it's
Just put a target on the guys.
Let's be friends.
Oh, there are one thing I need to correct. Can you give me your note? Because I did one mistake towards the end of the class. The cosine theta, sine theta, something I take it derivative. You fixed it, right? One is not fixed. It's not fixed. Yeah, so good. I don't know what that is. See, this is just correct this part. We said EAF is D, I think LAF cosine theta times IF over dt. This is what I wrote on the board. I put it LAF omega. Just remember theta is omega t plus delta, right? Delta 0. I'm not sure if they call it delta or delta 0. I think we call it delta 0, I believe. So d theta, when you take it derivative, it's going to be, derivative of this one is going to be, this is omega t, is going to be omega, and there's a minus here. Derivative of cosine is sine. This is what I wrote it there. IF, I'm putting IF capital because the current is sinus, it's a DC current, just I'm putting that one. So LAF omega IF sine theta. See, this one is I made a mistake. This two there, you need to correct your note. You need to correct it. And still, if you look at it, this is the EAF max, right? This is the EAF max. This is the sinusoidal function, right? This part is the maximum value. So basically, EAF RMS is going to be omega IF LAF over how much square root of 2? This is a 2 pi f IF LAF over the square root of 2. I think it's going to end up 4.4 for IF LA. So this is where we finished, and we came up with the equivalent circuit of the machine and all those kind of. Now we're going to continue from here. See, I'm going to put the circuit back again on the board. For the motor case, if you remember, it was like this. We had an R. This is the armature. This is the resistance of each phase, the stator. We have an XS or JXS. This is the synchronous impedance of the machine. And we have EAF. The one I calculated here, the RMS value. And here is going to be the terminal for the motor case, IA or armature. I call it IA or I call it IA. I call it IA. It's going there, and we call this one I think RA. But so let's write the KVL again one more time here. So I have two sources here, right? I have a one VT which is connected to a three-phase source, right? And this is the back EMF, induced in the machine, right? EAF. So let's consider this one with an angle of 0. I'm going to select this one as my reference, right? VT is my reference. Now let's write the KVL here. VT is equal to RIA plus JXS IA plus how much EAF? And this EAF is a phasor. It has an amplitude, this much, and the angle. We're going to calculate that angle, keep in mind. So let's calculate the EAF. EAF is going to be VT minus RIA minus JXSIA, right? Let's plot the phasor diagram for this machine. Let's say this is a VT, right? I assume the VT, what is it? The angle of VT is how much? 0. Is something with a 0 angle. I can select one of them as a reference, right? Phase A voltage, I consider it as my reference angle, right? Now, so, and let's assume, for example, IA is this way. For example, IA is like this, right? Is a lagging power factor, right? So, I want to find the EAF. I have the VT minus RIA. This is the RIA, right? Let's start with the other one. Let's start with this one. JXIA. So if this is a IA, right? What is this? This is a JIA, right? 90-degree rotate this way. Or I have a minus JIA, right? It's going to be different, right? Right? And this excess now is a factor, how much, 2 times, 3 times, 0.5, whatever is the excess. So basically, this is my IA. I need how much? Minus JXSIA, right? So here, if I'm positive, I'll go this way. Negative, I'm going this way. So this is the IA. So negative, I'm going this way, right? The direction of the JXSIA is going to be like this. Minus JXSIA. It's going to be like this, right? So basically, it's going to be a vector like this. I need to make it perpendicular to this. Right? Minus JXSIA. And what else? Minus RIA, right? I think that's like, right? So this is the RAIA, right? In the same direction with IA. But I have a minus RAIA. It's going to be opposite of that, right? It's going to be like offside. I should put it parallel with this one. So what is this? This is the EAF, and we call this angle delta. We call this angle delta. This is synchronous motor. I plotted here. There are 4 cases. When I finish the generator and we go toward the end, I'll talk about 4 cases. There is a generator overexcited, underexcited, and there is a motor overexcited, underexcited. But this case, one case just I put it together. Now, if you look at here, delta here is negative, right? Delta is negative, correct? See, this is a 0, right? This is 0. This one is here, right? Delta is negative. And this is the power factor, right? This is the phi is the power factor, right? Cosine phi is the power factor. You have terminal voltage and you have the current. The difference between these two, the phase difference, cosine of phase difference is going to be the power factor, right? So this is a phasor diagram for the motor case. Now I want to put it in the generator case. What is going to change for the generator case? Basically, EAF is going to be equal to VT plus RAIA plus JXSIA, right? And this current is going to be the other way, right? So if it's a generator, you just write it here. This is the motor. When the motor is like this. This is because the current is coming to the machine, right? If it is a generator, the current is leaving the machine, right? So EAF is going to be VT plus RAIA plus JXSIA. Look at this one here, EAF is smaller than VT, right? We can see clearly EAF is smaller than VT. But let's look at here. Let's plot this one. Again, this is the VT. And this is the IA. And this is the phi, right? So we are going to have how much? RAIA. It's going to be RAIA, correct? RAIA usually is much smaller than XIA because X is what, like ohm, something like that. R is what, 0.5 ohm, sorry, 0.1 ohm, something like that. So the next one is going to be how much? This is the JXF IA. And this one is EAF and this is it, right? And you can see here, delta is positive. Delta is positive. Just, I'm going to stop a little bit. For the next quarter, the power electronics too, there are 2 labs. I think right now they have an overlap with the 188. I don't know, 188 and 180. Arnold sent the emails, it was wrong. Just let me correct. They said it's not necessary to attend the lab, you have to attend the lab. It's mandatory. You should be in the lab. You treat it exactly like a lab. But what he meant was we can reschedule that from 8 to 10:30. So that way, if you have a class, you can finish that one, and you can go start 8 o'clock. Those when they don't have the class, they can start 7 o'clock. They still keep it open. But for those when they have a class, you can start 8, and still I think 2 hours would be enough for the lab. They are mostly simulation lab. Basically, yours would be 8 to 10. It's not you can go or not. You have to go to the lab. Just to let you know, if you're registering for that course, you have to be present over there.
It was my understanding Arnold was taking 180 also.
Yeah.
So,
Arnold, let me tell you, if the class wants to start, Arnold has to follow the class. If he doesn't want to be TA, we'll find somebody else. But he has to be there 7 o'clock, unless everybody in the class and we say we start, I don't know, 7:30 or whatever, 8 o'clock, whatever. That way he can manage it. He has to manage that one with his class. But his first priority is if some people in the class, they want to start 7, because we put it in the schedule 7 o'clock, he has to be there 7 o'clock. But for some, this is just working with you guys. For those ones, maybe they didn't register for that lab because of the overlap with the class. You know, we will start a little bit later. For those ones you want to have the lab that day, you can start 8 o'clock. I'm not sure his class is from when to when? 6:30 to 8?
6:30.
6:30, yeah. So they can start 8 o'clock. They can start the lab 8 o'clock, you know, not 7, you know. This is something Arnold should have put in the schedule already, you know. But, you know, it's a little bit late. Because I want to make it clear to you guys, it's not kind of arbitrary to go to the lab or not is mandatory. You have to be there, you have to treat it like a real lab, you know. It's a simulation lab, but there are lots of work to do, lots of simulation to do, and we're going to add more to the simulation lab. You guys will become kind of perfect with the, you did the balk boost, balk, to flyback, those kind of things. We'll give you examples with the control loop, to design all those kind of things with the control loop, you know. So, just I want to say what the email you sent last week, you know, to be corrected, you know, I was last week or this week. So, phasor diagram of the synchronous machine. Well, for the motor case and for the generator case, you can see delta is negative. I'm going to talk about this delta a little bit later, you know. Keep in mind. For motor, delta is negative. For the generator, delta is positive. We'll talk about this one. What does it mean? Actually, to not keep you waiting, delta positive is generating active power. This is using active power. But we'll get to the equation, you know. If you remember toward the end of the power system course, I had some equation for two systems. We had delta. That's exactly like this one, you know. If delta is positive or negative, means it's consuming power or it's generating power. So now the next thing is the synchronous machine, you know, test. Like a transformer, like a induction machine, we need to be able to measure the RA, we need to measure XA. This is not like that one, there's no XM, not those kind of things. There are two parameters, RA and XS. RA is very simple. How we can measure RA? Like a DC test for the induction machine, right? The stator will connect it at a star or delta, whatever you want. Usually they connect it at a star. And you put a DC source there, you can measure the current and you can measure the voltage, and it's going to give you the RA. But how to measure the XS? XS is the one we are going to explain. We'll explain RA also. But the one is going to be a little bit more tricky is the XS, to see how we can measure XS. So the first one is going to be DC test. So it's a synchronous machine. Synchronous machine test or parameter. One is a DC test. DC test, you know, we connect we have the stator circuit, right? And we have a roller circuit. I don't care about the roller circuit right now. It's going to be a roller like this, connected to the shaft. But we're not going to move the machine. The machine is stationary. We connected this one to a DC source, right? And how much is the RA? This one has a RA value, RA value, RA value. So basically, VDC, 2RA is equal to VDC over IDC, or RA is equal to VDC over 2IDC. So we know how to measure the resistance of the armature. We need to get to the measuring the XS. So for XS, we have to do two tests like the other. Open circuit test and short circuit test. Let's look at those tests. So open circuit, we mean the armature circuit, or they call in this case, in DC machine, the rotor is called armature. In the synchronous machine, the stator is called armature. But either we can call it armature or we can call it stator. The stator circuit is open. So basically, we have a circuit like this. We have, let's say,